This is the last lecture. We study C28, Hamilton's equations. Number one, we consider the motion of the harmonic oscillator, whose equation of motion is this. We recall that F equals ma, this F equals mass times acceleration. The net force applied to a harmonic oscillator is the restoring force, where K is the spring constant, minus X is the negative value of the displacement of the harmonic oscillator from the equilibrium position. If we move this one to the left-hand side, we obtain the equation of motion. Here, m is the mass of the particle. A. Derive the equation of motion by employing Newton's way. Newton's second law states that this, and we have obtained the equation of motion, same as given here. B. Integrate the equation of motion over the interval to find the potential energy. Let's see. Potential energy can be obtained. By the way, we expressed m double time derivative of position vector minus kx. This is F. We recall that potential energy is defined by V0, that is the value at x0 as a reference point, and minus from x0 to x f dx. This is the definition of potential energy evaluated at an arbitrary position x when the force is conservative. Because the definite integral uniquely exists, and the potential energy is well defined up to a constant that is arbitrary. So this is given in here. We would rather rewrite this one, replace this 0 with x0. Wait a second. Okay. So we rewrite this one into the original form, and we integrate both sides from x0 to x over x. Then this part is a mass acceleration dx integral from the reference point x0 to arbitrary point x. The right hand side has minus k. This is a trivial integral of a polynomial 1/2 of kx squared subtracted by x0 squared. Because this is a force, the right hand side is work done by the conservative force. So as a result, this is the reference point value of the potential energy subtracted by the potential energy at arbitrary point. As a result, we can read the potential energy from in here. It is by definition, and we can read the value of v of x that always contain 1/2 kx squared, and it is undetermined up to an arbitrary constant, that is an arbitrary real number. Because the particle makes an infinitesimal displacement dx, we can rewrite this one dx is a velocity multiplied by differential time difference. So acceleration multiplied by the displacement can be written in the form that this is dx. So because of change of variable, it's better to rewrite this one at time when the position is at x0, time when the position is at x. Uh, by the way, because there is a, it's okay. So let me correct this one. All right, I have replaced this value with corresponding time. According to the Leibniz rule for the derivative of a product, we find the product derivative of product is a dot b plus a b dot. We substitute for this x dot. This x dot squared is 2 times x double dot x. Therefore, x double dot multiplied by x dot is 1/2 time derivative of velocity squared. We know this one very well, that it is corresponding to the overall factor of the kinetic energy. Let's see. We replace this one with the time derivative of velocity squared, and derivative's integral is, or you should have replaced this one with x0, 2, and t of x0, t of something like that. All right, so we have derivative and integral. Therefore, this identity operation, and we substitute time at x, and x when x equals x0. So at x, its velocity is 1/2 mv squared, evaluated at that point, subtracted by the value of the kinetic energy evaluated when the particle was at x0. Therefore, this is nothing but the difference of the kinetic energy from the initial position to the final position. So this is also called the Coriolis work kinetic energy theorem. So when the force is conservative, just like in this case, the potential energy is well defined as a function of a position of the overall constant that can be shifted arbitrarily without modifying the theory. As a result, what we have found is that this is the difference of the kinetic energy, and that is also identical to the difference of the potential energy of the negative sign with opposite sign. As a result, this is the difference from x0 to x, and this negative value of the difference from x0 to x. So if I move this one to the left hand side, that the difference in this one becomes a t plus v at evaluated at x subtracted by t plus v evaluated at x0 equals 0. That means the sum of the kinetic energy and potential energy that is conservative. Conservative means it's independent of time, independent of position. So this is called a conservative quantity. This conservative quantity is called the total mechanical energy, and we call this relation the total mechanical energy conservation. Work kinetic energy theorem is valid in any case. However, it is not always true that the work done by some force is expressed as a conservative force as an integral. It is only if it is a function of a position. So definite integral is well defined. In that case, the total mechanical energy is conserved. Next, we consider the case that by multiplying the equation by, this is the displacement, the equation multiplied by displacement, then we compute the work. Show that the equation of motion reduces to the form total differential of the Hamiltonian, where H is the total mechanical energy and it is also called the Hamiltonian. Okay, so we multiply x dot to the equation of motion, and we find this equation is we recall that the total mechanical energy, that is the sum of the kinetic energy and potential energy. And sum of the kinetic energy and potential energy is independent of time, so its derivative must be zero. But it can be shown directly from the equation of motion because this is nothing but this one is this and this one is this. So this is from this equation of motion by multiplying start velocity, that is to compute the power, and that represents a very simple equation. Time derivative of the total mechanical energy is zero. By the way, in fact, our Hamiltonian is formally not expressed in terms of 1/2 mx dot square. Instead, we know the P equals mv. That's a linear momentum. And when we call the total mechanical energy as Hamiltonian, it's better to write, it's officially, formally, we have to write in this form. So P squared over 2m plus potential energy is the Hamiltonian. All right. So the Hamiltonian's total time derivative is zero. This is the conservative force. We recall that the Lagrangian is kinetic energy subtracted by the potential energy. So the formal definition of the Hamiltonian is to transform the Lagrangian under this very specific transformation that is called the Legendre transformation. Please remember that the Lagrangian is a function of x and x dot, and Hamiltonian is a function of a position and corresponding conjugate momentum, that is a linear momentum in our case. So the linear momentum in our case is nothing but the velocity derivative of the Lagrangian, that is the linear momentum. Okay, do you remember that? F equals ma. Ma is a time derivative of linear momentum. And force is minus a gradient of potential energy. And this one is nothing but the gradient of, let's simplify to a one-dimensional problem. Minus round x potential. So it is a derivative of kinetic energy minus potential energy. And this is this is Lagrangian. Lagrangian is T minus V. Okay, so because kinetic energy is independent of coordinate, in the Cartesian coordinate system, we have this force is identical to the spatial derivative of Lagrangian. And the right-hand side, this linear momentum is partial derivative of Lagrangian with respect to velocity. Here it is. Okay, so that's the reason why we have the equivalence between the Newton's laws of motion and Euler-Lagrange equation. So because this linear momentum is the partial velocity derivative of Lagrangian, so we have this P replaced with this round L over round X dot. All right. After that, at the end of the day, we have to replace this X dot, with something like that, because P equals mx dot, mass times velocity. Anyway, we would like to see what happens if we make use of the Hamiltonian to derive the equation of motion. First of all, we would like to keep using the least action principle, that the action that is the time integral action that is the time integral of Lagrangian is stationary if a physical system follows the natural path that is allowed by nature. Okay, we vary a certain path by a delta x, this fictitious, imaginary. We imagine deviation from this physical path. In that case, the velocity changes in a similar manner, and that is change in the velocity due to the modification of the path from the physical one to an imaginary one is just the time derivative of the variation of the path. We apply the variation of this integrand that would appear in the evaluation of the action. Hamiltonian is here as a function of x and p, and we have x dot p, the variation of this and variation of momentum. In addition, because the Hamiltonian is simply a function of x and p only, variation of the Hamiltonian can be made by making use of chain rule, because h is a function of x and p only. Okay, so we substitute this variation rule to find out the variation of the Lagrangian, because we would like to see what happens to the least action principle, not with Lagrangian, but with Hamiltonian. So we substitute this to find out the variation of the integrand in the action. These two are copies. And then we have negative sign, and we just copy the variation of the Hamiltonian, that is a function of x and p only. As a result, we find that this one is delta x dot p, and this is p time derivative of delta, and this is a total time derivative of p delta x subtracted by p dot delta x, right? This integration by parts, or we can make use of Leibniz rule to reproduce this. As a result, this one is replaced with this term and minus p dot multiplied by delta x. So this one and this one can be combined to find that this one. Another contribution that depends on delta P is here and there. So we combine these two pieces, variation in terms of X and P. We substitute the variation of the Lagrangian into the definition of the action. So action's variation that is evaluated from T1 to T2 along a path, a certain path x of t, to x of t plus the variation of the path. We find that this term is a total derivative, and after the integration, what we find is a momentum multiplied by the variation of path evaluated at two endpoints. We recall that the variation must be made only if the time is or this time is not the one of the endpoints. Beginning and endpoint must be fixed without variation. If we vary the initial and final position, then we change the problem. What we want to find is it is physical. There is a physical path, and I'd like to find what happens if we modify the motion from a physical path by a little amount. But the actual start and the end point must be fixed. If we shift this one, our problem is changed. As a result, this first term does not contribute at all because the variation of position at endpoints is not allowed. Therefore, what we find is the variation of the action is the following integral. We again require that the action should be stationary along a physical path. So near the physical path, from the physical path, if you vary both the linear momentum and position by a little amount with arbitrary value, this derivative should be zero. And this variation should be arbitrary along any kind of variation. This one should be a stationary value to satisfy that the action is a least value. As a result, for any undetermined unknown coefficients, this should be zero. That means the coefficient of those variables must vanish. That is this one is a zero and this one is a zero. We call this equation Hamilton's equation. Unlike the equation where Q is a generalized coordinate, this is the second order differential equation, and we recall that this is F, it is equivalent to F equals ma. So Newton's laws of motion and the second law, Newton's second law of motion, and Euler-Lagrange equation, they are equivalent and they are both the second order linear differential equation. It is not always a linear when the force is not a linear form. So second order differential equation. However, we find that Hamilton's equation is not a second order equation, but a coupled first order differential equation, a system of differential equation. And if we combine them together, we will reproduce this Euler-Lagrange equation and F equals ma. Let's see what happens if I make use of the Lagrangian for a harmonic oscillator. The kinetic energy is 1/2 mv squared, and potential energy is 1/2 kx squared plus some constant, but that constant doesn't matter because after taking the derivative with respect to either x or p, that constant that doesn't contribute at all. Let's see, it's a very simple relation, velocity, derivative, and velocity independent coordinate. All right, in a similar manner, this one, x dot and x, they are independent, and we have these differentiation table. What is the conjugate momentum? Conjugate momentum of this system, Lagrangian is here. We take the velocity derivative of Lagrangian to find out the conjugate momentum related to the coordinate x. So x dot appears in the kinetic energy only. The final result is mass times velocity. All right, find out the Hamiltonian. We now find linear momentum is mass times velocity. Hamiltonian can be obtained by making use of Legendre transformation, that is a px dot minus Lagrangian. Let's see, px dot minus Lagrangian. Lagrangian is a kinetic energy subtracted by potential energy. Okay, we remember the conjugate momentum p is mass times velocity. So velocity is a linear momentum. Velocity is linear momentum divided by mass. So Hamiltonian should be written in terms of x and p only, so we can replace x dot with p over m everywhere. Final value is O, nothing but the kinetic energy plus the potential energy. And it is completely expressed in terms of x and p only. So why don't we compute the Hamilton's equation? We derive the Hamilton's equation satisfies the least action principle that minimizes the action. So x dot is Hamiltonian's derivative with respect to the linear momentum, and p dot is Hamiltonian's derivative with respect to the coordinates with the negative sign. We list a table of the derivative involving linear momentum p and the coordinate x. These are trivial. Why don't we compute the momentum derivative of Hamiltonian? That is a p squared over 2m. That is a 2p. So cancel and p over m. Aha, this is a p over m. This is nothing but our previous definition of the linear momentum. Okay, and what's that? This is, next one, Hamiltonian's x derivative, the potential energy only, so 1/2 kx squared, this we have kx. Okay, so this is kx, substitute p dot equals minus kx. Aha, this is Newton's laws of motion. P dot is what? Force. Why? This is time derivative of linear momentum, and the linear momentum is mass times velocity, and that is ma. Aha, these two systems, this is system of first of the linear equations called the Hamilton's equations. They are equivalent system that is equivalent to the either Euler-Lagrange equation or Newton's laws of motion. Although the Newton's equation of motion and Euler-Lagrange equation of motion and Hamiltonian are all equivalent, nowadays it is we prefer either Euler-Lagrange equation or Hamilton's equation to direct the construction of Newton's equation of motion. Because Newton's laws of motion is always restricted to the non-relativistic classical mechanics. But if we consider the relativistic problem and electromagnetism and more fundamental problems, then we have to accommodate the relativity and quantum mechanics. So all of them can be considered only if we build a theory based on either Euler-Lagrange equation or Hamilton's equations that are stemmed from the least action principle. Nobody knows why the Hamilton's principle, the least action, should be satisfied. But the only thing we believe that is they are simple. There's no way to confirm why the basic rule of nature is so simple. Perhaps you can find the answer. Fundamental question. That's it for today, and that's it for the whole semester. Thank you very much for listening all of this lecture or escape from scientific absurdity. Thank you so much. That's it.